Okay, so here we go. We've got a nice, lovely mechanism, nitration, effectively of benzene. So, I explained the HCO arrows, how the mechanism works, and also how sulfuric acid acts as a catalyst. So, firstly, how do I generate my nucleophile? You know this equation, I'm sure. Well worth remembering because it's an easy mark. That's got me my electrophile there. So out come my electrons from the benzene ring to attack the nitrogen. That gives me my intermediate. Key thing to watch out for is that's carbon number 1, 2, 3. So my NO2 has got to attach on my carbon number 3 to give me the right product. And make sure you break the ring of electrons at that point. The electrons from the bond, the carbon-hydrogen bond, go back into the benzene ring to give me back my 6 delocalized electrons, and I make H+, and then finally my H+ reacts with this boy here that I made to give me back my sulfuric acid catalyst here so we can go through the motions again. Okay, so this is a new reaction that you won't have seen before, I doubt. Kind of freaks people out. So let's just write it. Benzaldehyde, which we know, we've just drawn it, reacts with potassium hydroxide. It's oxidized and reduced. So I've got an aldehyde that's been oxidized. That's going to become a carboxylic acid. I'll just make that a carboxylic acid. If it's reduced as well, it's also going to give me an alcohol, but remember this is in potassium hydroxide solution, so that is actually going to be the potassium salt there, and then hopefully you can see I've got 2 benzene rings out. I've got to start off with 2 of those guys there, and it should all balance out, I think. Yeah. Okay, there's a lot of information on this page, so I made it a bit smaller. I'll just expand a little bit again, so you can see. So it's given me some information about condensation reactions, which contain an amine group or methyl group attached to a carbon-carbon double bond. So any aldehyde group will react with either that or that to give me these compounds here. So hopefully you can see. Basically, if you've got this, that carbon just attaches to where the oxygen was to give me the double bond, and that nitrogen there just attaches to where the oxygen was on the aldehyde there. So I need to be able to predict the structure. So I'm going to start off with benzaldehyde, like so. If I go back, it's starting with NH2OH, which that's my NH2, it would just be an OH there. So it just affixes to where the oxygen was. So that goes to give me NOH, and I've got an H still there. So there's a lot of information on here. It's basically just taking this. So can you see if I've got an NH2 group there, the N just pops onto there and I'm in water, so the N replaces the O. If I've got a C double bond O there, the carbon next to it replaces the O there to give me that CH group. So that and 2 hydrogens go off to give me my water. So the first thing I need to do is take benzaldehyde, and react it now with NH2, but this one I've just replaced that with an N, and that becomes OH, like so. I've then got for this one benzaldehyde again, but this time, if I'm replacing it, I've got this set up, which is an example of the second one. That becomes the carbon there across the double bond. I'm still going to have one of those hydrogens, and that's going to give me C double bond O, OH, like so. Right, so this one's quite a tricky one. It's the same sort of setup here. That O is going to be replaced by that carbon there. And then I'm going to have C double bond O CH3 like so. But then I can have another benzaldehyde come along and do the same thing, because I've also got a C double bond O CH3 there. So the benzaldehyde is going to come and add on to this side of my chain as well. So that there is going to, that's going to stay. That carbon there is going to become C double bond. That's that. And that hopefully is the right structure. Right, so slightly nicer one now. We're going to look at some alkyl lithium compounds, which provides a source of the R- ion, which can act as a nucleophile. I need to show the mechanism by reacting the general. They're giving me R- here. You know, we've done this from when we used H-. That goes there, that one breaks to go there to give me C6H5O-, that becomes H, that becomes R. Stage 2 would then normally be you add water, which they've shown you here. We normally do it with water. That goes there, that breaks, although they don't want the mechanism. That sometimes helps us to show it, to give you your final product there. Okay, so hopefully if you looked at your product above, when you have to do this one, it's actually that bond that you formed, because originally this would have been your aldehyde, wouldn't it, if I get rid of that there and get rid of that one. So if you just draw this out, and then that there would have been replaced by your lithium, like so. Right, we're getting into question 5. How can we use the results from gas chromatography to predict the number of S's in the mixture and their relative proportions? Well, the number of peaks tells me the number of different esters I've got in the GC, and then the relative proportions are obviously told me by the peak areas that I get. The larger the peak, the more of the ester I had. Why would there be uncertainty? Well, because they're all esters, they're going to have similar retention times, so it may be difficult to tell them apart. Okay, then it's time for the spectroscopy question. I've been told what the molecular ion peak is, 164, and I've been given a hydrogen NMR spectrum here. Obviously, that boy is telling me I've got a benzene ring, mono-substituted, because he's got an intensity of 5 there. So I'm going to have that group there. It looks as well as though I have I've got an ester group. It's told me I've got an ester group. I now need to work out how I can, the relative shifts there and there. Okay, so I've marked on the spectrum where each of these come from. So obviously those are my 5 hydrogens coming off the benzene ring there. I've got an intensity of 5. This chemical shift here, about 2.2, shows a CH3 group. It's going to be a CH3 group. I've got an intensity of 3. Can't have any neighbour because it's not split at all. So next to a C double bond O. This peak here coming in about 2.8, intensity 2, CH2 group, which is adjacent to a benzene ring. And then here, this peak coming in at about 4.3 is a CH2 attached to an oxygen, which suggests that I have got, I've also got a CH2 group next to it as well, because it's split into a triplet. So it looks like these two guys are next to each other. So if we put this together, I've got my benzene ring there. Looks like that's my CH2 group there. CH2 group oxygen, C double bond O,